Okay, so I apologize in advance for the poor quality of this video. I'm just filming on my phone instead of my usual computer setup. But I got a question about this one, 1.5 to 1.6 assignment, part C. So the one about the firefighters. So if you're wanting to follow along, you should go to that assignment so you can see where I'm pulling this information out of, because I don't have it written down here. I'm just going straight into solving the problem. So we have two firefighters, okay, and it tells us some information about these two, their trips down the pole, okay? So it says one gripped the pole tightly so that he dropped at a constant velocity of 2.25 meters per second. So we'll call that firefighter 1. So think about what that means. He has a constant velocity of 2.25 meters per second. That means VI, yes, is 2.25 meters per second, but also VF is 2.25 meters per second. Constant V of 2.25 meters per second means this guy is actually moving in uniform motion. So let's just quickly define what's going to be positive and what's going to be negative. We'll call up positive and down negative. But what that means is that this guy has a V of negative 2.25 meters per second because it's down. And that is true everywhere. Yes, it's VI, but it's also VF. It's just V. Now the other one is a little more interesting. It's non-uniform motion. So this second guy, he holds on more loosely, which means gravity will actually be able to accelerate him down a bit, okay? But he's holding onto the pole, so it's not going to accelerate him down at a full negative 9.81 meters per second squared. He only accelerates at negative 3 meters per second squared, okay? And it says he starts from rest. So that tells us that VI equals 0 meters per second. Okay, and it's downward, of course. We don't know VF. It doesn't tell us VF. That's okay. Maybe we don't need it, okay? If you continue to read the question, what is the purpose of it? It asks you to find the distance that they travel. Now, it tells us that both poles are the same length, okay? So what we're looking for is D. Now, we could call it D1. Let's just go ahead actually and call this V1 because it's for firefighter 1. And firefighter 2, this will be V2 initial, an acceleration of 2, okay? So we could call it D1, we could call it D2, but since they're actually both the same thing, let's just go ahead and call it D, okay? Now there's another important piece of information in the question, and that's that it took them the same amount of time to go from the top of the pole to the bottom of the pole. So in other words, T1 equals T2. And if you want, you could just say T equals 1 equals T2 and T1 equals T2, and since they're both the same, let's just go ahead and call them T. If you want to, you can. I'm just going to keep them the same so that when we're working with them, it's a little bit clearer. Now that's actually all the information the question gives us, and it wants us to know figure out what is the distance they must have gone down, okay? And so there's not enough information here to just take this guy. For example, if you wanted to figure out D just from firefighter 1's motion, well, you would need T, right? Yes, it's uniform motion. So yes, this is one of those rare cases where we are allowed to use V equals D over T. However, we don't have T, so there's two unknowns in an equation that will never work for us. Here we have VIA and we want D. That would be great, again, if we had T or if we had VF. But we don't have either of those things, so that none of the 5 kinematics equations we have will work there. So whenever this happens, we're looking to cancel stuff out based on our 2 scenarios. So we hopefully are going to be able to get rid of some variables and cancel some stuff out until we find that we only have one unknown, being the unknown we want, D, okay? Now there's a few approaches to this, okay? So you could solve it like a system of equations from math, or you can find out what's equal in one and then set it equal to another. That's what I'm going to go for, okay? But there is more than one way to solve this, and there's more than one valid approach. So what I'm going to say is just that we need to rewrite our equations and variables until we have one equation with only one unknown. As soon as you have more than one unknown in an equation, it's not solvable, at least yet. You might have to go get that other unknown or get it in terms of something else. So let's start off here by analyzing firefighter 1. What do we know? Don't lose sight of the goal. We need to get D eventually, right? But what we know is that he's moving with uniform motion. He's not accelerating. So this is one of those very rare cases where we can say that his V1, is equal to D1 over T1, right? His speed is equal to the distance he travels over T, which yes is just D, okay? We'll just keep it consistent by calling it T1. Now, we know that the times are equal between the two, right? So let's see if we can get his time here, and then whatever T we get there, we know also applies to firefighter 2. In other words, if I manipulate this a bit, so if I multiply both sides by T1, to get V1 T1 equals D1, and then go ahead and just divide both sides by V1. There we go. Now we've got T1 is equal to D1 over V1. It might not feel like we're closer, but remember, T1 is the same as T2. So that actually tells us something about over here. We know that his time is going to be equal to D1 over V1 now, right? So T1 equals D1 over V1, but T1 is T2 because they took the same amount of time. All right, now that we've got this information, let's see if we can take it over to Firefighter 2 and get anything more useful out of that. So what have we got? We've got a VI, we've got an A, we want a D, okay? And VI is even 0, so when I see that D, VI, A, and we kind of have T, even though we don't have a number for T, we do have an expression for T. We've got D, VI, A, and kind of T. So if you go to your formula sheet, that should lead you towards this equation. VIT plus AT squared over 2. Now, of course, this all applies to 2. We could say D2, but that's just D for us, but it's definitely V2I, T2, just for the sake of that, A2 and T2, which again is the same as T1. Okay, luckily for us, V2I is 0, so we can just cancel that out as 0, and we're simplified a bit now to D equals A2 T2 squared over 2. But now look at what's just happened. T2 is D1 over V1. We found that out by analyzing Firefighter 1's motion, right? So what we can do now is plug that in here for T2. We can say D equals A2 T2, yes, but T2 is D1 over V1. So let's go ahead and stick that in there. Don't forget it's squared all over 2. Okay. Now look, something magic just happened, right? You can kind of see now, oh my goodness, we have one equation with only one unknown. We can solve this. If we play around with this, we only have one thing in this equation we don't know. See what we did there? We took one of the things we didn't know, we wrote it in terms of something we wanted to know, and then used that to get rid of it in the other equation so that we don't have to worry about not knowing the time, right? Now the only thing we don't know is D. So I'm gonna now change from calling it D1 to just being D again. I just put it in there so we could see where it came from. But let's go ahead and just rewrite that as D equals A2 times D over V1. It's still V1 squared over 2. Now we just have to play around with this a bit until D is isolated. So what do we got? We got D equals A2. D over V1 squared is going to be, they both get squared, so D squared over V1 squared all over 2. Okay, this is D squared, so I'm going to bring D over here so we end up canceling that too. But first, let's just kind of clean this up a bit. We're going to multiply by 2 and divide by A2 to get rid of that. So times by 2 to cancel that out, and then divide by A2 to get that out. Just make sure you do that over here too. Okay, let's just go ahead and simplify this a bit here. We've got 2 times D over A2. Okay, that's just multiplying the 2 in there is equal to D squared over V1 squared. That's all that's left over here. V1 being the velocity of, or the speed of the first firefighter. Okay. So now let's just go ahead and get D squared all by itself, and then we can worry about how there's 2 D's on either side. So let's multiply by VI squared. Whoops, sorry, V1 squared, not VI, V1 squared. We get 2D times V1 squared over the acceleration of the second firefighter is equal to D squared. Don't panic that there's a D on both sides, right? Because now we just want D by itself, so let's just go ahead and divide both sides by D, and we'll see what happens. Look, D is being multiplied, it's on the numerator here, so to get rid of it, we'll divide, which is the same as just putting it in the denominator. Now it cancels out, and we must do that over here. But look what just happened. D squared over D, well, D squared is just D times D, right? So D is being multiplied by D, but it's also being divided by D, so really it's not squared, and that one cancels. So let's just simplify. 2 times V1 squared, the speed of that first uniform motion firefighter, over the acceleration of the non-uniform firefighter, firefighter number 2, is equal to D, the distance. And look at that. We know V1, it's negative 2.25 meters per second, right? We know A2, it's negative 3 meters per second squared, and so all we have to do is plug that in. Now here's where you might be a little bit nervous because that was some weird stuff we did. We did some cancellation with formulas, got rid of variables. Let's go ahead and check that that actually worked with our units. okay? That's a free way to check that our manipulation does indeed make sense. So then just moving over here to do just a unit check. Okay, we have meters over seconds, and that's all being squared here. So we have meters over seconds, and that's all getting squared over. In our denominator, the only units we have are meters per second squared. So when we square meters over seconds, we square both, right? We square the meters and the seconds, so that's going to give us meters squared over seconds squared all over meters over seconds squared. And now we're dividing by a fraction, so maybe an easier way to see this is to then rewrite this when we divide by a fraction. Remember, that's the same as multiplying by the reciprocal, so this is really meters squared over seconds squared times, take the reciprocal, so flip that, so it's going to be seconds squared over meters. And then look at this, we've got seconds squared on top, seconds squared on bottom, so those are going to cancel out. And then we've got meters squared over meters. Remember, meters squared is just meters times meters, and then it's being divided by meters. So it's not really squared, it's just meters over, that cancels too. And look at that, we got units of meters. And this is good because we were looking for a distance, right? So we wanted to get units of meters. That makes sense, now we feel good. Leaving the only thing left to do, plug in these numbers into our calculator and see what we get. And so we end up, I did that, I got an answer of negative 3.475 meters, okay? So now we just stop, think, sig digs, all that kind of stuff, direction if required. Now it just asked for distance, but we got a negative, so that's a good thing as well, because remember, we defined down as negative and up as positive, and so of course the displacement they are covering is negative, right? They're sliding down the pole, so it's a good thing we got a negative, so we just have to worry about sig digs. We were given 2 in the question, so our answer should only have 2, 3.5 meters. If you wanted to write it as a displacement instead of a distance, it would be 3.5 meters down, but it just asked for distance. So there we go. Now again, there are multiple valid approaches to this. You could have tried to get your things to cancel out differently, but the main goal here, the main idea, was to write variables in terms of other stuff that we do know until there's only one thing that we don't know in a valid expression.